Hello. In this lecture, I am going to continue the Bohr's model of atom. In the last lecture, I have derived the expression for radius of the nth orbit, which is given as n square h square 4 pi epsilon naught by 4 pi square m z e square. Okay. Except n and z, all other things are constant for an electron. So if you substitute those values, you will get radius of the nth orbit equal to radius of the first orbit into n square by z. This formula is applicable for hydrogen atom as well as hydrogen-like ions. For hydrogen atom, the radius of the first orbit was found to be 0.529, which is called the Bohr radius. Okay, and the formula become Rn equal to radius of the nth orbit equal to 0.529 into n square by z. You will get the answer in angstrom units. Right, and we also found that the delta R, that is the gap between adjacent orbit. The gap between adjacent orbit is equal to radius of the first orbit divided by z into 2n plus 1. Okay, as n orbit number increases, okay, the gap between adjacent orbit also increases. Okay, so the gap between first orbit and second orbit is small, right, and the gap between second and third is little large. The third and fourth is even larger. So as we move away from the nucleus, the gap between adjacent orbit increases. Okay, then second quantity that we discussed is velocity of the electron in the nth orbit, and the formula for this is 2 pi z e square over 4 pi epsilon naught into n into h. This is the formula for velocity of the electron in the nth orbit. And if you accept z and n, all other things are constant. If you substitute those constant, we get velocity of the nth orbit equal to 2.18 into 10 to the power 6 z by n. Okay, you'll get the velocity of the electron in the nth orbit, and you'll get the unit as meter per second. Okay, using this formula, you can calculate velocity of the electron in the nth orbit. Okay, then we also derive the expression for the time period for revolution. Okay, time period for revolution, that means what is the time taken for an electron to complete one cycle, okay, in the orbit, right, which is given as 1.5 into 10 to the power minus 16 n cube by z square. Using this formula, you can calculate, you'll get the answer in seconds. You can calculate the time period of revolution, that is to complete one revolution, okay, what time the electron takes. Okay, that you can calculate using this formula. We also derive the expression for frequency of the revolution. Frequency of revolution means number of revolutions that electron makes in a given orbit in 1 second. Okay, that you can calculate using the formula 6.66 into 10 to the power 15 into z square by n cube. Using this formula, we can calculate the frequency of revolution of the electron in a given orbit. Okay, yeah, so all these things we discussed in the last class. Then we also derived the expression for energy. The expression for energy in Bohr model, we get like this: En, energy of the nth orbit, equal to minus 2 pi square m z square e power 4 over 4 pi epsilon naught the whole square into n square h square. This is the formula for total energy of an electron present in an nth orbit. Except z and n, all other things are constant for an electron. So if I substitute, I'll get energy of the electron in the nth orbit as minus 13.6 times z square by n square. We will get the energy in electron volt per atom. This is energy for one atom. If you want energy in joule per mole, you can also write like this. Okay, you have to do some conversion. I'm not going to do that because it's a very simple one. So it is nothing but minus 1312 into Z square by N square, you will get the energy in kilojoule per mole of atoms. In kilojoule per mole. Okay, this will give you energy in kilojoule per mole. Right? Remember all these things. Now, if I plot energy versus N, how the plot will look like? It is something similar because the remaining things are constant. So En is inversely proportional to N square. Okay, so if I plot En versus N square, I will get an hyperbolic relation, right, between these two. Okay, then the most important one is the relation between En and Rn. How energy of the electron in the nth orbit is related to the radius of the nth orbit. Okay, yes, we can do that. En equal to minus 2 pi square m z square e power 4 over 4 pi epsilon naught the whole square into n square h square. This is the energy formula. Now what I'm going to do, I'm going to divide this by this quantity. I'll multiply this by 4 pi epsilon naught and I'll divide this by 4 pi square m z e square. So this is the expression for radius of the nth orbit. So we have to make we have to multiply this by 4 pi square m z e square over 4 pi epsilon naught. Okay, I'm just multiplying by 4 pi epsilon naught by 4 pi square m z e square, and I'm also multiplying with this quantity so that these two things cancel. You will get the relation, the equation remains same. Okay, now see, why did I do that? 4 pi epsilon naught, I can cancel this square. Then we can cancel this pi square m 1 z and square I'll cancel here, and e square I'll cancel this 4 and make it 2. Okay, and here we have 2, 1 2 are 2, and here 4 we have, so 2 2 are 4. Right, so what we left with is En equal to, so we have z, we have e square in the numerator divided by here we have 4 pi epsilon naught, and this quantity is nothing but radius of the nth orbit. So we get 4 pi epsilon naught into radius of the nth orbit into 2. We have 2 here. Okay, so now see, En and Rn are related by this equation. En and Rn are inversely proportional here. Okay, for a given atom. Okay, right? If Z is fixed and all these quantities are constant, right? For a given atom, En and Rn are inversely related, right? So if you plot En versus Rn, you will get an hyperbolic equation, right? A hyperbolic curve. Let me draw and show you. So what I'm going to do, I'm going to plot energy, that is En, in y-axis, and in the x-axis I'm going to plot Rn, right? And here, if you plot as Rn increases, see, as Rn increases, radius of the nth orbit increases, this quantity will decrease. Okay, because Rn is in the denominator, as Rn increases, this quantity will decrease. In mathematics, decrease means negative. So negative of negative become positive. That means energy will increase. As Rn increases, energy increases. So as Rn increases, energy increases. Listen, if Rn is very, very small, okay, say for radius of the first orbit, if I put, I'll get the lowest possible energy. Okay, in negative, right? Negative value of energy. So as Rn increases, the energy increases in this manner. When Rn goes to infinity, right? When Rn becomes infinity, energy becomes 0. So energy will attain 0 when Rn approaches infinity. Okay, so this is the relation between energy and the radius of the nth orbit. And the energy values are negative. Okay, keep this in mind. Now, what is the lowest possible value of energy? See, the energy expression is this: En equal to minus 13.6 into Z square by N square. You will get the energy in electron volt. Okay. For hydrogen atom, suppose if you take hydrogen atom, for hydrogen atom Z value is 1. Okay, therefore this formula becomes En equal to minus 13.6 by N square. You will get the energy in electron volt. Okay. Now, what are the possible value of N? Possible value of N are 1, 2, 3, 4, etc. N can take only integer values 1, 2, 3, 4, etc. If I put N equal to 1, I'll get the lowest possible energy or the ground state energy. So if I put N equal to 1, right, let us say this is N equal to 1. If I put N equal to 1, I'll get energy, something here. Okay, so this is the energy of the first orbit and the ground state energy of the electron, which is minus 13.6. Right? Let me do it in the next page so that you'll get some clarity over that. So energy, right? This is energy, right? Energy, when electron is present in the affinity of nucleus, okay, the energy of the electron is negative, right? See, the energy of the electron in the nth orbit, okay, it is negative value. What does this value indicate? What does the sign indicate? It indicates that the electron is bound by the nucleus. Okay, whenever electron is bound with the species or with an atom or with a molecule, then the energy of the electron should be negative. Okay, this is what the Bohr formula conveys. Okay, and when n is equal to 1, if I put n equal to 1, you will get the lowest possible value of energy, and the energy is minus 13.6 electron volt. What's the next higher energy? N equal to 2. If I put n equal to 2, you will get the energy as minus 3.4 electron volt. Okay, in the formula, if I put n equal to 2, see, it's very simple. If I put n equal to 2, 2 square is 4. So 13.6 by 4, you will get minus 3.4. Then if I put n equal to 3, 3 means 3 square. 3 square is 9. 13.6 by 9, you will get 1.51 electron volt. So the next level energy, which is n equal to 3, the energy of this level is minus 1.51 electron volt. The next higher energy is n equal to 4, and the value of energy here is minus 0.85 electron volt. Okay, and the gap between, so like that we can calculate energy of the any orbit, energy of the electron in any orbit using the formula. Now, what is the gap between the first level, the ground state level, okay, the energy of the electron in the first orbit and the energy of the electron in the second orbit? What is the energy gap? The energy gap is minus 3.4 minus of minus 13.6. You will get 10.2 electron volt. Okay, so the gap between, energy gap between an electron in the first orbit and electron in the second orbit is 10.2 electron volt. And what's the gap between these, the second and third? Minus 1.51 minus of minus 3.4. If you do, you will get the answer is 1.89 electron volt. Similarly, if you find the gap of this, you will get 0.66 electron volt. See, what does this indicate? It indicates that the energy gap between the first orbit and the second orbit, or energy of the electron in the first orbit and energy of the electron in the second orbit, this gap is very, very large, 10.2. As you move away from the nucleus, the energy gap between adjacent orbit, okay, decreases. See, this is very important. The gap, okay, the distance between adjacent orbit increases as you move away from the nucleus, whereas the energy of adjacent orbit, okay, decreases. Okay, this is a point you should keep in mind. Okay, yeah. So these are all the various energy levels, right, possessed by electron in the hydrogen atom. Okay, these are all quantized energy levels, right? So Bohr by introducing that the angular momentum of electrons are quantized in hydrogen atom. Okay, based on that, he could explain, okay, the hydrogen spectrum to some extent. Okay, yeah. So I stop here. In the next class, we'll discuss about hydrogen spectrum. What is hydrogen spectrum and what are the information that we can get from hydrogen spectrum. We'll discuss that in the next class. Okay, thank you for listening.